let's start today's session. We'll solve some problems, and if any confusion is there, a question, then we'll solve it. So, primarily we'll solve problems from assignment 6, and which primarily deals with Rasba spin orbit coupled model and spin current basically. We had Rasba Hamiltonian plus alpha r. Alpha r is the Rasba spin orbit coupling coefficient or strength, and then sigma cross k type uh, interaction. So we had something like sigma cross k, and this is the along the z component. So this is the Rasba Hamiltonian. Now, this is of course sigma 0 is here identity matrix. So sigma 0 is 1 0 0 1, and then sigma x is 0 1 1 0, sigma y is 0 minus I 0. So if you write the Hamiltonian in the matrix form, we will have h bar square k square by 2m, and alpha r ky plus I k x alpha r ky minus I k x. So if we derive, in order to evaluate the eigenenergies, we just need to solve this determinant equation minus, let's say these are eigenmodes, energies. 0, so which will give me square minus alpha r square and ky plus ikx ky minus ikx equal to 0. This we can write as minus lambda square And then so I need to get out of this square, which will be uh, plus minus alpha r, and then root over kx square plus ky square. We assume that alpha r is positive, and then lambda will be h bar square k square by 2m plus minus alpha r k. We can write, so where k is root over kx square plus ky square. This is, so the parabolic term was also like that. We have never explicitly written in terms of kx, right? But so these are the eigenvalues or eigenenergies. And if you draw this, so initially we had parabolic term. This was, let's say, for free energy parabolic. Sorry, free electron gas. Mhm. Completely parabolic. And then now we have something like, this is one sector. So so this is, let's say, one sector which remain like this. Okay, and this is k, and this is energy, and another sector is kind of like this. Okay, so actually let me draw with different colors, then it will be, I think, more clear. So this was E and K. So let's say this is one sector, and I mean one eigenenergy, let's say, and another one is looks like this. So these should be symmetric, but nonetheless. So blue color represents plus eigenenergy, and red color represents minus eigenenergy, E minus. Okay, and when I plot this is with respect to k, which is mod of kx square plus ky square. Okay, in fact, this is not appropriate plot, in a sense that k cannot be negative, right? This is the mod of some square quantities, so I should not draw this sector when I draw with respect to k. So this can only go. Okay, so this is the Rasba models eigenenergy. Okay, so this is with respect to the mod k, and if we draw with respect to any of the crystal momentum which can be negative, things will be more clear. So this is, let's say, kx, and with respect to ky, the plots will be similar because these are symmetric in both kx and ky. So I'll have this plot, So this is one band, let's say, and this is another band. Okay. So if this is the spin up sector, let's say, and then it will be the spin down sector. Okay, so this blue region or the blue uh, lines represent the spin down, and then red represents the spin up. This is the energy. So this is actually kind of, so this is the effect of Rasbata. If we think of a parabolic dispersion, free energy parabolic, only h bar square k square by 2m term is there. So then if we plot with respect to kx and energy, this will simply be parabola, and this is for both spin down and spin up. Now if you, so this is parabola, let's say, sorry, free energy. And then if we plot free energy but then Zeeman term, so sorry, I'm repeating, it's not free energy, it is free electron actually. Free electron plus Zeeman term. Let's say we have applied some magnetic field. So in the free electron case, spin up and spin down both have the same energy, but for this case it will be kind of shifted with respect to the zero energy, and this will also be, and then this will be spin up, let's say, and this is going to be spin down, because then with respect with Zeeman term, what will really happen is that energy plus will be h bar square k square by 2m, and let's say plus spin is there, so which Zeeman term is minus mu dot b. So if mu is along b, then this will lower the actual energy, so it will be kind of minus mu b, let's say. Mu is some magnetic moment of free electron, and then E minus will be, or rather I should represent it as E minus, just for consistency with the Rasba model also, and E plus will be, so okay, let me write and then repeat, plus mu b. But we need to remind ourselves, or remember that E minus is for up spin and E plus is for down spin, because if the spins are aligned along the magnetic field, the energy gets lowered, which is this band, this one, and if the uh, spins are anti-parallel to the applied magnetic field direction, then the energy is going to be higher. Okay. So we had this free electron case, and then if we apply Zeeman term on top of the free electron, considering the spin Zeeman coupling, then we'll have this kind of band structure. And but without this Zeeman term, if we have free electron, so this is actually free electron plus Rasba spin orbit coupling, Rasba SOC. Then we are not going to have this kind of up and down, but rather they will be mixed. So the spin character is going to be mixed, and that's what it means. So spin orbit coupling mixes the spin character of a band. So if you see this one, this first plot, energy versus k, you are not able to say that this is the up only down spin and this is the up spin. Okay, because when you are with respect to the k, when you're drawing with respect to some component, then we can draw some kind of, again, parabola which are shifted in k space, which will have distinct spin character. So throughout this band we will have up, and throughout this band it will have down. Okay, we can also evaluate the uh, so eigenvectors the conventional way. So I'll not explicitly derive, but I'll just tell how to derive. So let's assume x is some eigenvector satisfying that hx equal to those energies and x. So these are two component spinor. So I'll have some Hamiltonian, and then a b, and then energy matrix, which is 2 by 1. So this will be E plus and this will be E minus, and then again AB, and we'll have some equation, right? So this is a 2 by 2 equation. So we'll have equation 1 and equation 2, and we have to solve those equation in order to find uh, so let me solve that. Actually, I mean, complete few processes. So this is h bar square k square by 2m, and again same thing, alpha r kx minus iky alpha r kx plus iky. So it will have h bar square k square by 2m a, and then plus alpha r kx minus iky b equal to e plus uh, a, and then alpha r kx plus iky uh, a plus h bar square k square by 2m b equal to e minus of b, right? So let's get this equation 1 and this is equation 2. Now we need to solve equation 1 and 2 for a and b. Okay, and we also need to, and this was the first process, and second process is we need a square plus b square equal to 1. So this is called normalization. Okay, so the the wave functions are going to be straightforward. Actually, you can easily evaluate that by doing these two processes. You just need to solve for a and b, and while solving, and we will also impose some constant that a square plus b square equal to 1, just to have normalized wave function. It turns out that if we have any 2 by 2 Hamiltonian, let's say, uh, any 2 by 2 Hamiltonian can be written as combination of all the sigma matrices, Pauli matrices, and the additional identity matrices, as a combination of sigma 0 and then sigma x, sigma y, sigma z, right? So these are generic Hamiltonian. So I have some Hamiltonian which may be H0 of k. K is vector which can also depend on kx and ky, right? Uh, if we restrict it to 2D, but in general this can be extended to 3D also. There is no restriction, kx, ky, and kz. And h0 of k is some quantity, let's say k dependent, which is associated with sigma 0 diagonal terms, and then hx of k associated with sigma x, each y of k sigma y plus hz of k sigma z. So this is the most general form of any 2 by 2 Hamiltonian. And H0, I mean each of k's have some different forms depending on the particular system. And so it turns out that we can easily have some general wave functional form and energy form. Once we parameterize this h0, hx, hy, and hz in terms of let's say a kind of spherical coordinates. So what we assume is that hx is some hk which is different from this h0, hx, and hy. So this will be denoted by h super sorry subscript k sine theta k. This will be clear in a minute why I am writing sine theta k and cos phi k. Similarly, hy equal to h of k sine theta k sine phi k, and hz equal to simply hk of cos theta k. Okay, where hk is given by root over of h0 of k square plus hx of k uh, square plus hy of k square. Sorry, I missed something. So this will not be h. This is hx and this is hy and this is hz. Okay, h0 is not there in hk. And this Hamiltonian, let's give it equation 3. Okay, so for equation 3, any Hamiltonian 2 by 2 Hamiltonian of the form equation 3, the eigenenergy is epsilon or simply E is given by h0 of k plus minus root over of hx of k square plus hy of k square plus hz of k square. This is h0 of k plus minus, sorry, simply hk, right? Mod of hk, or simply you can write hk itself. So this is general expression for energy for any 2 by 2 Hamiltonian. Given that, so if you have given any 2 by 2 Hamiltonian, you just need to figure out or segregate the terms with sigma 0, sigma x, sigma y, sigma z, and any of them can be 0 as well. I mean, we can have Hamilton. So for comparison, let's say for Rasba we had this term, this three terms, right? H0 of k was simply h bar square k square by 2m, free particle parabolic term. Hx was associated term with sigma x, which was I think minus alpha ky. So yeah, so sorry, plus alpha ky. So this was the term with sigma x, and this was the terms with sigma y. Minus alpha or kx was the term with sigma y. So for this model, h0 is simply free particle parabolic term. Hx is alpha r ky, and hy is minus alpha r kx, right? So once you segregate this, you will have this general kind of energy eigenvalues given by, let's say, equation 4. And if you solve this, follow this process, these two process for this Hamiltonian 3, you will have general expression of eigenvectors for any 2 by 2 matrix, let's say, and those let's denote it by u plus of k. This is k, and you will have e to the power minus I phi k. So I have not still defined what is phi k theta k. Now we will define. and this sine theta k by 2, and then u minus of k. So this is corresponding to the E plus eigenenergy, and this is corresponding to the U minus is corresponding to the E minus eigenenergy. So this will simply be e to the power minus I phi k sine theta k by 2, and then cos minus cos theta k by 2. Okay, so this is corresponding to the E minus. So this, let's call it uh, 5 and 6. Okay, where theta and phi are defined as, so sine theta k is given by hx of k square plus hy of k square by h of k, and then cos theta k is simply hz of k by h of k. Sin phi k can be defined as hy of k by h hx square plus hy square, and then cos of phi k is given by hx of k, hx of k square plus hy of k square. And one important thing to note is that, uh, so let me write and then I'll see, I will explain. So h0 of k don't appear in eigenstate. Okay, and this has important consequences, or rather important, I mean, physical explanation in the context of topology, Berry curvature, and so on. H0k is simply the diagonal term, which in our case represents parabolic free electron dispersion, and it doesn't appear in the wave function, I mean eigenstate rather. Okay, for that h bar square k square 2m, we usually have simply the free electron or free particle part e to the power I k dot r, which I am not writing in equation 5 and 6. Let's see. And it will turn out later that if we calculate that topological or simply band geometric quantities, in one of the classes I introduced that uh, something called Berry curvature, Berry phase, and then there was some lot of other things such as quantum metrics and so on. Those things are not affected by H0. Okay, since these Berry curvature, quantum metrics, and so on, these terms are actually properties of wave vectors, not only the eigenenergies but also the wave vectors or wave functions, let's say. Uh, so so this h0 term do not appear in wave functions, and consequently in Berry curvature and quantum metrics itself. And this is one of the reason, or one of the way that we can understand that in free electrons or free particles, these band geometric quantities such as Berry curvature, quantum metrics are identically zero, because it has no contribution of hx, hy, and hz. So we only have h0, but then h0 doesn't appear in eigenfunction. Berry curvature, quantum metric being properties of eigenfunction, these band geometric quantities are zero for free electron case. Okay, so these equation 5 and 6 are actually very general uh, expression for eigenstate for a given Hamiltonian of equation 3, which we can always write any 2 by 2 given any 2 by 2 Hamiltonian. So we just need to find out or segregate the terms which is h0, hx, hy, and is z, and then we can determine these eigenvalues and eigenvectors. Okay, so the next question is next we are going to calculate spin resolved density of states for Hamiltonian of Rashba spin orbit coupled system. Okay, so the general expression for density of states is that, so density of states, so density of states simply says ki how many states are there per unit energy, let's say, okay, which is actually given by, simply you can calculate it from, so GE at any particular energy, let's say E, how many number of states are there, which is can be calculated by summing over all the k, and this is E, and let's say we are trying to have some for plus band or plus A spin states, then we will have plus of k. So this is the delta function, and what it really says is that delta function peaks at exactly at some point, otherwise it is zero. So it has infinite peak, and this distribution is very small. I mean, it is actually, it's an exact line type of thing at some particular k point in k space. Let's say this is my kx and this is my ky, and we have e plus of k, which is a function of k, and in the k space of the or the blue region, we're just counting how many state is there with energy E. So this is my given. I need to calculate density of state at some energies. Okay, I have given some energy, which will be a number. Okay, and I have dispersion relation epsilon of plus k, which is not same in k space as you have seen in graphene or any other material for that matter. So it varies in k space, and you have given some energy. So if this delta peaks counts how many times that energy is getting repeated. Okay, so yeah, that's the main point. So this is sum over k space. So you are considering all the k points in the Brillouin zone, and this delta will give you only one. I mean, this delta will give you one only when there is E equal to E plus of k, or in general, if I write for both spin state, E plus and minus k, right? So whenever this is the argument of the delta function is 0, then we will have 1, and then otherwise it is 0. So that means at that energy point, how many of states is going to be there. Okay, so that's the physical way, or the, I mean, why do we write a sum over k and over the delta k. But so now to calculate the density of states for both spin state up and minus, so what we need to do is, that, so, what we need to do is 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 that, so, what we So in two-dimensional system, this g of plus minus of energy, let's say g of plus minus e, can be written as k plus minus, or rather, so if we go conventional way, then so g plus minus of e is going to be sum over 1 by 4 pi square, right? And sum over, so this will be d2k, and delta of e minus e plus minus of k for plus state and minus state. Okay, and we have e plus minus of k equal to h bar square k square by 2m plus minus alpha r of k. Now this k, this d2k is including dkx dky, and when I write k here in the energy expression, it is actually kx square plus ky square. Okay, so k is simply kx square plus ky square. So now if I take 2D polar coordinate system where this is ky, this is kx, and somewhere this is, let's say, k, and this is phi, polar coordinate, sorry, polar angle, then we can write k as simply k cos phi, kx as k cos phi, and ky as k sin phi, right? Since this is polar, in the polar angle this is symmetric, this expression, then we can directly write g plus minus of e will simply be some just converting or going from Cartesian coordinate to polar coordinate. So in the Cartesian coordinate, sorry, in the polar coordinate, it becomes, the area element becomes d dk d phi, and delta of e minus e plus minus of k, right? And phi limit is of course 0 to 2 pi, so 2 pi comes out, because energy plus minus is going to be independent of phi. So we all have k, mod k and k square. So mod k is already kind of kx square plus ky square, so cos square phi plus sin square phi is going to give me 1, and this is also k square. So we are left with k dk and delta of energy minus e plus minus of k. So 4 pi square, so 1 by 2 pi k dk delta of e plus minus of k. Now to further evaluate this, we need to know one delta function property, which says that integration of delta of, let's say, some function delta of x and f of, or rather more general, delta of x minus a and f of x, let's say. So this is one property which will, and this is integrated with respect to x. So property 1, this should simply be fa, because whatever the value of fx may be, if we are not at the x equal to a, this term will be 0. So f can only pick the term where the delta function is 1 or non-zero, let's say, because delta function is defined like x of a, sorry, delta of x is simply 1 for x equal to 0 and 0 everywhere else. Okay. And the second property is delta of x, sorry, delta of fx rather. Delta of fx can be written as xi delta of x minus xi by mod of f prime xi. So So delta of fx is some function of x. We can write xi are the roots of fx. Okay, xi roots of fx equal to 0. Let's say this equation's roots. So this can be written as delta of, so we had delta of fx, we converted it to sum over all the roots delta of x minus xi and divided by mod over f prime, which is the derivative of fx with respect to x at xi. Okay, so this we can utilize in this equation. Then it will be g plus minus of e equal to 1 by 2 pi sum over k dk, and this we are going to write sum over ki. Let's say ki are the roots of e minus ei, e plus minus k. Okay, so let's focus on the first uh, plus band, then it will be easier to follow. Similarly we can do for the minus band, because otherwise there will be a complicacy, because for plus band e plus there might be some roots which may not be applicable for the minus band. Okay, so this is ki, and delta of k minus ki by divided by e minus, sorry, e prime, or rather be more careful. So del k derivative of e minus e plus of k at k equal to ki. Okay, okay, so now our first work is to determine the ki. Ki are the roots of this equation, e minus e plus of k equal to 0. That means e plus of k at e is some energy where we want to find the density of states. Okay, so we have h bar square k square by 2m plus, for e plus it is only plus alpha rk, and then energy. This is a quadratic equation, so h bar square k square by 2m, or rather let me simply k square plus 2m alpha r by h bar square k minus 2m e by h bar square equal to 0. So this will be simply minus this term, k will be minus 2m alpha r by h bar square divided by 2 into a, so there is nothing, so 2 into 1, and then plus minus b square, so minus sorry 2m alpha r by h bar square whole square minus 4ac, so 4 into 1 into c is simply minus 2m energy by h bar square. Okay, so this will be, we can have two roots because this is a quadratic equation in k. So minus m alpha r by h bar square. This term we sometimes call k alpha, which is related to the uh, spin orbit coupling strength alpha. I'll tell what it really means, k alpha. Okay, for now let's not write that. Plus minus of, so this 2 square I take common and take out of root over, so which will be again 2, and this will cancel out with these two, and again we are left with m alpha r by h bar square whole square minus, again I take out this 4, we're left with 2me by h bar square. Okay, so these are the two possible k, I mean root for positive energy. Okay, now we need to find what is physical, what is not physical k. When in the polar coordinate, the radius cannot be negative, right? K is my radius in the polar coordinate. So if k is negative for any root, it is not a valid solution. It is not a feasible solution. You notice that this, when we take minus sign, this is going to be negative because m alpha r by h bar square. So okay, this term is definitely greater than this term, mod of this term, right? Because all are positive. Let's say epsilon is positive, we assume. Okay, you are determining the density of state at some positive energy. Again, remind that we have band structure for positive energy state like this. So this was E plus, this was E versus K. So this was a positive, right? So E has to be positive, so E is somewhere here, let's say. So then E is positive, so let me write E is positive, and then this term is going to be greater than definitely this term, because everything is positive inside, and this is simply, this term is already there here. So when there is only negative sign, there is this solution, that k equal to minus m alpha r by h bar square minus of m alpha by h bar square whole square plus 2me by h bar square is not valid for e plus of k. So we are trying to find k, right? This intersection. So this is E plus, and this is some constant energy where I want to find density of states. So k is simply, we are trying to find this point or the solution. K cannot be negative also, so this is not a valid solution. So the only solution left for us is minus m alpha r by h bar square plus square plus h bar square. Okay, so in this expression sum is not needed. We only have one root, one physical root. So we have g of plus of, at some energy E, 1 by 2 pi, and then we had k dk delta of k minus ki. We had sum over ki, all the roots, and del k of E minus E plus of k mod at ki. Now ki is simply this one. Okay, so we have 1 by 2 pi. Not integration is not needed because we are evaluating the delta function, right? Again, I use this property 1, integration of some delta function and then some function. It only picks up where the delta function have non-zero value. So it will simply be ki, so ki, and then del k of E minus E plus of k at ki, and this ki is given by this expression. So this will be 1 by 2 pi minus m alpha, or rather let me simplify more. So E is some constant independent of k, so this will simply by ki, and this is also mod, so simply d E plus of ki by del k, right? No, I should not write that actually. Del e plus of k by del k at ki, and this is mod. Okay, so this will simply be 1 by 2 pi, and uh, ki, and if we, since we have e plus equal to h bar square k square by 2m plus alpha r k, so d derivative with respect to k will simply be h bar square by 2m 2k plus alpha r, right? So this will be h bar square by m k plus alpha r evaluated at ki. Now if I put the values, then 1 by 2 pi and then minus m alpha by h bar square plus root over m alpha by h bar square whole square plus 2me by h bar square, and then when I write this k and alpha r, then we will have only this term actually, root over m alpha by h bar square plus 2me by h bar square. Okay, so this is the density of state at some energy, which is definitely positive because positive energy states only do not have any e plus, do not have any negative energy. So this is the expression for, let's say, positive spin states also. Okay, and similarly we can derive uh, the density of states for the negative energy states also, E minus. Okay, and throughout this we assume that E is positive. Okay, so whenever it says that we need to evaluate density of state at some energy, so we need to evaluate, let's say, G of epsilon. For Rasbach case at least, it needs to be mentioned, or for that matter, any general case, it needs to be mentioned that energy is positive or negative. The reason I'll just explain. So, so this is the positive energy, right? E plus, and this is the negative energy, and this is k, and this is simply energy. Now at some energy you need to give or sorry, you need to calculate the density of states, let's say. So this is where, let's say, you want to calculate density of states, some energy state e, e0, let's say. Now the point is, whenever we are evaluating that the root of those function, delta function, you are essentially finding the k points where e plus exactly equal to e0, and that's, for this case we will have this point, and for e minus we'll have this point, right? So this is the k alpha, sorry, k root ki kind of, and this is another ki for minus state. So as you can see from the figure itself, that for positive energy, plus state only have one intersection, so only one root should be there. From the figure also we see that only one root should be there, and in the math, from the mathematics also we said that this is not a valid state because it was representing k minus. So effectively my calculation also gives me that yes, there will be one root which is feasible and another one is unphysical, and this will be applicable even for the e minus case also. We have explicitly calculated for e plus, but this will be true for e minus case also. Now let's say you are at a negative energy. Okay, so at somewhere, so minus e0, let's say. Now at minus e0 you do not have any density of state, you do not have any density of state for the positive energy state e plus. Okay, because it is just like that, this energy band is only greater than 0. Now for negative energy states, sorry, e minus, we have two intersection, right? So we should get both the k to be valid, and we can actually find out that both k are valid description or the valid solution of the quadratic equation. So if you solve e minus equal to, let's say, e0, where e0 is itself negative, okay, e0 is itself negative, this also we can say e0. So here e0 is positive, here e0 is negative, okay. So if you solve this equation with this E0 negative condition, then we will see that there will be two solutions, Ki1, let's say, and Ki2, let's say, and both will be valid, meaning both will be greater than 0, and yeah, so both will be greater than 0, which is also seen in this graph. So that's how we can derive the spin polarized density, spin resolved density of state. So this was, let's say, for the plus spin, and then similarly we can derive for the minus spin. It will be the spin resolved density of state. Okay? And for positive energy states, which is E0 greater than 0, we'll have only, I mean, we'll have contribution from the both E plus and E minus, and for negative energy e0 less than 0, we'll have only contribution, we'll have contribution only from the negative, sorry, e minus state. Okay, so next question. Okay, so there is another question. uh, Hamiltonian of a single electron in two-dimensional xy plane, I mean in the xy plane, in presence of both a uniform magnetic field in z direction and Rasbach spin orbit coupling. So the Hamiltonian for Rasbach spin orbit coupling will simply be h bar square k square by 2m, and then plus alpha r. We had sigma x k y minus sigma y k x. So this was the Rasbach Hamiltonian, and then we need to add another term which will represent the uh, uniform magnetic field in the z direction. So let's, so the term will actually be minus mu dot b, but since b is along z direction, so we'll only have minus mu z bz, right? And mu z can be positive, let's say, for spin up state, and mu z can be negative for spin down state. Okay. Okay. So this is the Hamiltonian. So for solving this Hamiltonian, I mean, to make it more easier, you can just assume that, okay, Hamiltonian for spin-off state will be all of these terms, and then minus bz, mu z bz, let's say, and then Hamiltonian for negative terms will be again all of these terms plus mu z bz, let's say, okay. Or rather, you can also write that mu z is plus mu 0, let's say, or simply mu 0 is something else, permeability, so simply mu for plus state, and mu z is minus mu, let's say, for minus state. That way you can also do, okay? And then you can again you need to do all the process of uh, for spin off state and spin down state separately. So next question. The assignment 7 questions are all, I mean, from the whatever discussed in the lectures. It was directly kind of taken from that. There is no new questions. In fact, all of them actually have been solved in the lecture itself, so I will not go through that. Lectures are very nicely given, so which are really clear. Okay, so let's stop for today, and we'll again meet next